Hi folks, we are continuing with the Unit 1 Day 9 lesson, and we're on video number 2 for Day 9. We're going to start talking about linear combinations of vectors, and that's something that we have already been doing. In particular, we've been doing that with our 3 special unit vectors, the I hat, j hat, and k hat, because we have been able to write any vector in R3 as a linear combination, which just means a scalar multiple of each vector added all together. So can we add up these vectors or some scalar multiple of those vectors and get to any other vector in our 3D space? And of course we know that we can. We are going a certain amount in the x direction, a certain amount in the y direction, and a certain amount in the z direction, and that will get us to any point in R3. So what it means to have linear combinations of these form a basis for space, or R3, so 3-dimensional space, because any vector in that space can be written as a linear combination of I, j, and k hat. So those are the main vectors that we've been working with and writing linear combinations of, but it can actually apply to any vectors. So we can write linear combinations of any kind of general vectors, say u and v, and we can use those vectors to get to lots of different places. And we're going to, like I said before, see a lot more of that in Unit 3 when we start looking at equations of lines and planes. But for now, what we want to do is see, can we write vector w here as a linear combination of vector u and vector v? So what that means is, can I have a scalar multiple of u plus a scalar multiple of v and somehow get to vector w? So the best way to do that is just to try. So I'm going to have 2 scalar multiples. I'm going to call them a and b. And we will either be able to do it and find values for a and b, or we won't and we'll find something that doesn't work. So what we're going to do here, and I'm just going to state that a and b are any scalar real number values. So I'm going to take a look and write this in component form. So I'm going to have a times -2, 4, 5 plus b times 1, -3, 2 equals vector w, -8, 18, and 11. So what we really want to do is break apart the x, y, and z components of these equations. So if I simplified this, I would have -2a, 4a, and 5a, and then I would have here b, -3b, and 2b. So you do not actually have to show all of these steps, but I feel like it's maybe valuable to do it once. So here I would have -2a plus b if I'm adding the x components of the vectors together, and then 4a minus 3b for the y components, and 5a plus 2b for the z components. So at this point, we've simplified pretty completely on the left-hand side, and I see that my x component is written in terms of a's and b's, and that must equal the x component of vector w. And then my y component is written in terms of a's and b's, and that must equal the 18, the y component of vector w. And then my z component of this simplified form must equal 11, because that's the z component of vector w. So what I'm going to do is actually to form 3 different equations I'm going to say that negative 2a plus b must equal negative 8. 4a minus 3b must equal 18. And 5a plus 2b must equal 11. So this looks, we've got multiple equations, each with two unknowns. This kind of looks like a grade 10 substitution elimination question. The problem is that we have three equations and two unknowns, and our values for a and b, we obviously know that we could pick two equations and find a and b, but those a and b values would have to work in the third equation. So this is a really important step here. Once you get to this step, you are going to use two equations to solve and check your answer in the third equation. So it's not just a matter of solving any pair of these. You have to make sure that the answer you get will also work for the third equation. So I'm going to take the first equation here and I'm going to multiply this by 2. So I'm going to do elimination. So I'll get negative 4a plus 2b equals negative 16. My color coding is getting a little bit out of control here, but then I add down, I get negative b equals 2, so b equals negative 2. So I'm going to take that and sub it back up here. Negative 2a minus 2 equals negative 8. So negative 2a, I'm running a little bit short on space here, so I'm just going to skip a bit of steps, equals negative 6 when I bring that 2 over and divide by negative 2, a equals 3. So I have a solution here. I figured out if I'm just considering the first two equations, I get a solution of a equals 3 and b equals negative 2, but I have to go over and actually check and make sure that that holds true for the third equation, because this means if a equals 3 and b equals negative 2, the x values will be equal and the y values will be equal, because those were the equations that I used to solve this. But that doesn't tell me if the z values are equal, because if I had, say, 3 times vector u, so if I had 3 times vector u minus 2 times vector v, and the x's were equal and the y's were equal to the w, but the z's weren't, then it's not a linear combination. So we have to go back and we just do a little left side, right side. Check. So I'm going to put in a equals 3, so 5 times 3 plus 2 times b is negative 2. So I get 15 minus 4, which is 11. So it is a linear combination. So it's asked, yes, it is a linear combination, and we can just say what the linear combination is. 3 times u minus 2 times v equals w. So that's saying, yes, you can write this as a linear combination and telling what the linear combination would be. The next topic we're going to look at is called spanning sets. So this is sort of a way of saying, can you have a linear combination of two vectors and be able to get everywhere? And this is, in this course, really relevant to R2. We know that with the vectors I hat and j hat, so we use those. we can get anywhere in R2 with a linear combination, some multiple of I hat and some multiple of j hat. That means a I hat plus b times j hat can equal any vector in R2. We can get any vector by a linear combination of those two. There is something similar that we could look at as any three vectors, because we know we had to add k hat to get to any spot in R3. So it is possible to say, can we have three vectors that can get anywhere in R3? But the use of that is a little bit beyond the scope of this course, but it's very similar and just kind of extended into another dimension there. But I hat and j hat are not necessarily special. They're easy to use because they're unit vectors right along the axis, but there's actually an infinite number of sets of two vectors that can span R2. So we could have, just to kind of draw it out, because we can draw R2 pretty easily, right? We could have I could have like vector u and vector v, like that. And I could get anywhere on R2 using those two vectors. I would have some scalar multiple of u and some scalar multiple of v, and I could actually get anywhere in R2. But it doesn't work for every pair of vectors. So we're going to look at two different cases. So the first problem here says determine if the following sets span R2. So we've got two different examples, and this is A. So we want to know, I'm just going to kind of arbitrarily say u is 3, 2, and v is -1, 5. So if these two vectors span R2, then we should be able to find some multiple of u plus some multiple of v can be any vector in R2. We can get to any point in R2 using multiples of these vectors. So if u and v span R2, then a times vector u plus b times vector v is any point x, y. So that is a general, I'm not going to sub in a particular point because obviously that wouldn't be proving this, but I should be able to get an x and y value for different a's and b's. I should be able to get to any possible x and y that I want. So we're just gonna, again, just gonna try this. I'll put in my u and v in here. So I would have a times vector 3, 2 plus b times -1, 5, which is x, y. And again, just kind of simplifying on the left, I'm gonna skip a step just to save a bit of space. I hope we're all okay with saying 3a minus b would be my x if I multiply the a in there and the b and then added together. And then the y's, I'll have 2a plus 5b. So again, I'm going to pull apart and make two different equations, one with the x's and one with the y's. So my equation for the x components is 3a minus b equals x, and my equation for the y's is 2a plus 5b equals y. So what we're going to do is to take a look. What we want to do is see, can we solve for an a and a b so that we could figure out what that a and b would be for any particular case of x and y. So we're basically just going to try and rearrange this and solve for a and solve for b. Okay, so can we get an expression for A and B in terms of X and Y? Basically, if we knew the X and the Y, could we figure out what the A and the B are? So if we knew a particular point, any point, can we solve for an A and B value there? So we're going to try. And again, this is just substitution and elimination. I think I will just isolate the B here. So I'm going to say B equals 3A minus X, and then sub that back in. You could use elimination as well. I think this one gets a little bit messier than the last one. So here I get 2A plus 15A minus 5X equals Y. 17A equals 5X plus Y. And A equals 5 over 17X plus 1 over 17Y. You could keep that all as one fraction, that's fine too. So again, a little bit messier, but I'll sub that back in here and solve for what B would be equal to. So 3 times this kind of messy thing, 5 over 17x plus 1 over 17y minus, I see a need for a common denominator in a second here. So I'm going to have 15 over 17x plus 1 over 17y minus 17 over 17x. Getting a little squished in. Just going to draw a line there. So I think that I end up here with negative 2 over 17x plus 1 over 17y. So this is not a real pleasant answer, but it does give us an expression that if you knew an x value and a y value, you could certainly substitute those in to these equations and say that you could find your A and your B. So yes, this set does span R2 because you can find your A and B values given an x and y. And B is negative 2 over 17x plus 1 over 17y. So the opposite of that, and I think probably an easier way to see this, is what happens if it doesn't span. So that's what's going to happen in this one. And we're going to do the same kind of idea. So we're going to say I have vector u, which is 4, negative 1, and vector v in this case is negative 12, 3. And we're going to start the setup of this the same. We're going to say we're going to pick some real numbers and just say I want a times u plus b times v to equal a general x, y coordinate point. Now, if we have a times 4, negative 1 plus b times negative 12, 3, and I'm going to go through the same kind of idea. I'm going to get 4a minus 12b and negative a plus 3b equals x and y. And now again, I'm going to pull these out, create two different equations. I think I'm using the opposite colors this time, but I think that's going to be fine. So here I get 4a minus 12b equals x, and negative a plus 3b equals y. So again, I'm going to want to solve and figure out if I can find an expression for A and B in terms of the X and the Y. So I'm going to probably just do substitution again here. So 3B minus Y equals A. I'm going to take that and sub it up into equation number 1. So then 4 times 3B minus Y minus 12B equals X. So we're going to keep going and solve here. I get 12B minus 4Y minus 12B equals X. But now I run into some trouble because I'm trying to solve this for B, but all of my B's just canceled out. So I get negative 4Y equals X. So I can't solve this for A and B because my B's disappeared. And if you look at these vectors, what do we notice? This is a scalar multiple. So U is V is a scalar multiple of U. If we multiply this by -3, we get the second vector. And what that means is that these vectors are parallel. So if they're collinear or parallel, they're not going to be able to get to all of the places on my XY plane. They're not going to be able to get to all of the different points in R2. They'll only be able to get to the points along that same straight line. So these vectors are not really helpful at getting or spanning this R2 plane. They can't get everywhere. They can only get places that are those scalar multiples. So here we would say these vectors do not span R2. And actually the reason that they don't is that they're parallel, because 3 times vector U equals V. -3. So, as we've seen, if you have a pair of non-zero, non-collinear, so not scalar multiples, then those vectors will span R2. If you have vectors in R3, any non-zero or non-collinear vectors will actually form a plane in R3. And in R3, if you can write a third vector as a linear combination of the first two, then those 3 vectors are what's called coplanar. So if 2 vectors form a plane and a third vector can be written as a linear combination, which is what we saw in the earlier example, then those would be coplanar. Okay, and this is the part that I said was a little bit beyond this course. If you have 3 non-coplanar vectors, they will span R3, and they'll allow you to get to any point in that 3-dimensional space by using a linear combination of 3 vectors. But again, that's a little bit beyond what we're really going to cover here. I have one last example. I have 4 points, and I want to know, this is a really good thinking question, do they lie on the same plane? So I'm just going to start and draw 4 points. And try not to make it look like a square. So flipping back here, remember in R3, coplanar means on the same plane. If we can write a third vector as a linear combination of 2 other vectors, then those vectors are all coplanar. So they would be all on the same plane. So let's try to use our 4 points and make 3 vectors. And then if we can write the third vector as a linear combination of the first 2, then we know that those would all be coplanar. Okay, so let's maybe just draw, and this is a little bit arbitrary. We could definitely pretend that goes to D. Let's see if we can write, say, AD as a linear combination of AB and AC. So can we write those as linear combinations of each other? So first of all, I'm going to need these vectors. So AB, 2 minus -1 is 3, 5 minus 3 is 2, 7 minus 4 is 3. And AC is -3 minus -1. So -3 plus 1 is -2. 1 minus 3 is -2. And 6 minus 4 is +2. And then AD would be, where are we? 0 minus -1 is 1. -1 minus 3 is -4, and 2 minus 4 is -2. So what I want to see is, can I write a linear combination? So if I'll say A and B are real numbers, can I write A times vector AB, and this A and the capital A of my points are different A's. It is a little maybe bad notation here. I could have picked different variables. Plus B times vector AC, pardon me, equals vector AD. Can I do that? So let's give it a try. We'll have A times 3, 2, 3, plus B times -2, -2, +2, equals AD, which would be 1, -4, -2. So breaking this up, and I am, just to kind of save a bit of space, I am going to skip a little bit ahead and just jump right into my 3 equations. So the x equations, I would have 3a minus 2b equals 1. And you don't have to show all of the steps I showed in earlier ones, but you always can if you want. And here I have 2a minus 2b equals -4. And then I have 3a plus 2b equals -2. So remember, for checking coplanar, you're always going to be able to find a solution for the first 2 equations. We need to check that solution and see if it's true in the 3rd equation. That's the key of saying, is this going to actually work out? Is this going to be a true value or not? So this is actually lined up nice for elimination because I've got -2b and -2b. So I'll just write this underneath and subtract down. So I get -a, -2b minus -2b is gone, and -4 minus 1 is -5. So a is +5. Then if I pop that maybe in this other equation, 3 times 5 minus 2b equals 1. Again, getting a bit squishy there. So 15 minus 2b equals 1. -2b equals, bringing that 15 over, I get -14. So b is 7. Now I've come up with values for a and b that would give me a scalar multiple of the x values would equal 1, and these scalar multiple of the y values would equal -4, but we don't know if these scalar multiples of the z values will actually still equal -2. So we need to do our check of left side, right side check with the third equation. And it's not always, you don't always have to use like the X and Y equations and then check in the Z. It's totally arbitrary. You could use like the Y and Z equations and check in the X. It doesn't matter. I just usually kind of go left to right. So here we've got 3a plus 2b, and we want to know, does it equal -2? And I can see already this is not looking good. So we've got 3 times 7 plus 2 times 5, which is really, really not -2. So 21 plus 10, 31, that's not true. So we can say, therefore, points A, B, C, and D are not coplanar. Okay, those the vectors formed between those cannot be written as a linear combination. So this third vector in my diagram is not a linear combination of those other two. It's much harder to kind of draw and visualize in 3 dimensions, but the math will always follow through. And that is it for day 9, and that is it for Unit 1.